Good afternoon. My name is Leah, and today I'm excited to share my machine learning project with you. I chose to use decision trees to predict agricultural crop yields. For the next few minutes, I'll walk you through the motivation behind the project, the data and model used, and the insights I gained from the results. My project problem statement was, can we accurately predict crop yield based on data we have about historical environmental features? If so, this can help us with resource allocation, financial decisions, and future planning. This project produced a regression model that predicts crop yield based on historical features such as the country, crop type, and year. But why does it matter? Well, agriculture is sensitive to shifting weather patterns, soil quality, and geopolitical factors. Predictive models allow for proactive strategies in resource allocation, food distribution, and market forecasting. It enables agricultural stakeholders to make informed decisions about many aspects of agriculture, including crop planning, land use, and supply chain logistics. Ultimately, this contributes to greater food security and sustainability goals. For my project, I chose to do a regression problem. I chose this because the goal is to predict a continuous numeric variable, which is the crop yield, instead of categorizing inputs. On the right, you can see an example of what that looks like in the project. The target output is the crop yield measured in hectograms per hectare, or HG per HA. Hectograms per hectare is a key performance indicator in agriculture. It is a common productivity metric that standardizes agricultural output across regions and crop types. The crop yield prediction dataset was used for this project. The dataset originates from the Food and Agricultural Organization and the World Data Bank. The dataset contains structured tabular data with country-level information on crops and corresponding yields, making it well-suited for a machine learning model. Now we can go over the features and the target. For the features, we have columns such as the area, which contains the country name, the item, which contains the crop type, for example, maize, wheat, corn, the year, the average rainfall in millimeters per year, the amount of pesticides in tons, and the average temperature experienced in the area. The target variable is the crop yield, or the amount of harvest, in Hg per HA. For this project, I chose to use a decision tree. It was selected for its adaptability with categorical inputs, its interpretability, and its resilience to outliers. It was implemented using scikit-learn and Python libraries, some of which are pictured here. Initially, I explored using a neural network for crop yield prediction, but the dataset included high cardinality categorical features like country and crop. I had 101 unique countries, and neural networks often struggle with such inputs. Label encoding proved insufficient for capturing meaningful relationships. Given the structured tabular nature of this data, a decision tree model offered me several advantages. It naturally handles categorical variables, it's robust to outliers, which were very prevalent in my dataset, and provides clear interpretability through its branching logic. These qualities made it a fitting choice for revealing complex nonlinear patterns in the data. For a decision tree regressor model, I had several evaluation criteria to go through. Primarily, I used the root mean squared error, which penalizes larger errors, the mean absolute error, which measures average prediction deviation, and the R-squared score, which indicates how well the model explains variability in yield. These metrics helped to quantify the model's reliability and guided model development. How well did the model perform? Well, the decision tree delivered pretty reasonable predictive performance with an R-squared value of 0.957, especially considering the presence of outliers and high cardinality categorical data. The transparent structure of the decision trees enable us to gather insights into how specific features influence yield predictions. Now we will switch over to the Jupyter Notebook, which will give you a clear understanding of how to implement the decision tree. Now we can take a look at the Jupyter Notebook together. I wrote a little introduction with the file info and the project description with some context, and then provided a link to the dataset. To begin, we needed to import some modules. That includes the Pandas, NumPy, Matplotlib, Seaborn, and scikit-learn libraries. That created a data frame, which I titled Yield DF, and then I got a sense of the data by displaying the rows in the head and the tail. Next, I took a look at the shape of the data frame. That revealed that there are 28,242 rows and 8 columns, So a pretty good sized data set. I took a look at the max and min yield values, and that's the target variable, and that gave me a sense of what was typical for a yield in our data set. And I took a look at the year range, so I know that we're working with 1990 through 2013 as far as dates go. I looked at the info for the data frame, and that revealed that none of the columns seem to have easily spotted missing values, so they all have 28,242 non-null values, a pretty complete data set. I noticed that 2 of the columns, the area and the item, contained objects, so those are strings, and we'll be able to deal with those later on to prepare them for the machine learning model. I took a look at the column names and noticed that I have an indexing column. I described the data and rounded it to 2 figures to get a sense of what I'm working with. Once again, each column had 20,242 data points, so that checks out. And now we can move on to the histograms. First of all, we have the year, and my general findings were that the year is relatively uniform, suggesting consistent data collection. The crop yield is right skewed, showing that most regions have moderate yields, with some achieving exceptionally high yields. The average rainfall shows a multimodal distribution, so an up-down tendency, which suggests that the data spans regions with distinct climate zones. The pesticide use is right skewed, suggesting most areas use minimal pesticides while a few use quite a lot. And the average temperature displays multiple peaks, suggesting differences between weather zones which might impact the yield. Up next, I had the box plots, and from the box plot, I saw many outliers, as you can see. I decided to take an iterative modeling approach, initially not addressing these outliers, because I believe they offer the full complexity of weather patterns. Weather can be extreme and unpredictable on some years, and that tendency might temper or exaggerate the predictions from the model if I keep these data points in the data set. So ultimately, it might better reflect real-world variability by keeping these data points in, and there's also a huge number of them, so I feel like getting rid of them or tempering them in some way might skew the data set and cause the machine learning model to not pick up on patterns that might actually be really important for the bottom line. And then next, I created some scatter plots, and I visualized the yield versus rainfall, the yield versus temperature, and the yield versus pesticides. So this gave me a sense of the yield, which is the target variable, compared to different features. And I'm starting to see some trends emerge, but it's a little bit difficult to see given the vast number of data points. So I went ahead and created a heat map as well, and that reveals how strongly the pairs of variables in the dataset are linearly related to one another. And as you can see, there's not very many strong correlations, which is a good thing for a decision tree. Decision trees look for trends that are nonlinear, so if this were highly linear data, it may be better suited to something like a linear regression model, but in this case, this is actually looking really great for our decision tree. And then, part 2 of 4, we have data preprocessing. And first off, I dropped the unnecessary indexing column. So the unnamed :0 got dropped, which was just a duplicate of the indexing numbers. And then I checked for null values, once again, and none appear present. I checked for duplicates, and it seemed like I did find some duplicates, 2,310, which represents about 8% of the data. So it's definitely something to address, because just dropping them could lead to important information loss. And then upon closer inspection, even though the columns like temperature or rainfall repeat across the crops, they act more like features describing the environment and each crop is experiencing. So we essentially have a data set where the unit of observation is crop and year, not just the year. So they were all worth keeping. And then I renamed the columns and rearranged them for clarity, counted unique values, and considered grouping the data, but found it would not impact my final result substantially. So then, up next was labeling coding. Since my data has two categorical columns, the country and the crop, I had to label and code them. This converts an object column into a numerical one for the algorithm to better process. In my case, with label encoding, I wanted to be sure that the model wouldn't mistake country A equals 1 as less than country B equals 2. So I tested out creating a cutoff point for the top countries using a cumulative frequency threshold, but I found it did not substantially impact the bottom line, so I didn't worry about that. I then generated a correlation heat map to get a quick overview of the data's structure and the interplay between the numerical variables once again, and this time color-coded using Seaborn. I visualized some relationships using scatter plots, once again, such as rain versus temperature, pesticides and yield, and pesticide and rain, but since the data are nonlinear, there were only very loose relationships depicted. And then to finish preprocessing, I split my data set into a training set and a testing set. This allows me to evaluate the model's performance on unseen data and avoid overfitting. The training set is used to teach the decision tree the underlying patterns in the data, while the testing set acts as a simulation of real-world scenarios, and that gives me insight into how well the model would generalize beyond the data it was trained on. This step is very crucial in validating that the model isn't just memorizing the training examples, but can actually make accurate predictions in practice. I ended up using a 75-25 split, which is a reasonably common approach, alongside splits like 80-20, ensuring the model has enough data to learn while still leaving a sufficient portion of the data for objective evaluation. Scaling was also done. I used the standard scaler. This helps to ensure that the features are on a similar range. Features like pesticide use or rainfall, in my case, had larger numeric scales, and that gave them a potential of disproportionately influencing the model. So this scaling helps to ensure that doesn't happen. And now we're ready to model the decision tree. To do this, I used the decision tree regressor and gave it a max depth of 11. I stored the original feature names and then made a prediction using the machine learning model. I then converted the series to NumPy arrays before reshaping it, and this produces a predicted value and actual value, which are displayed down below. And then we're ready to evaluate the model. With max depth, increasing it, I found increasingly good values for R-squared, but I had to be really careful not to overfit. For real-world scenarios, using the hyperparameter tuning would give me the ideal fit for the model without having to do it manually, so that was an option I explored. But I was pretty happy with the R-squared score I got. My hand-tuned model had a coefficient of determination pretty close to 1, and the closer to 1 the value is, the better predictions it makes. And my score was a 0.957, which is a pretty strong model score. And then I also calculated the mean squared error, and from it derived the root mean squared error, and that value tells us how far the error is in the original units of the target variable. In our case, this means that my predictions would be off around 17.5 thousand Hg per HA for the yield. Then I visualized the predictions of the training set by using Matplotlib to create a scatter plot showing the actual versus predicted yield of the training set. The closer the points are to the perfect prediction line, the better the model fares. And so as you can see, it came pretty close in this set, and then the same can be said for the testing set. The observation points follow the perfect prediction line fairly closely. I used Matplotlib to also plot a few single features against the target variable, in this case the actual yield and predicted yield with the average temperature feature. And we can see that the orange x's, which are the predicted values, are overlapping or closely aligning with the actual values, which are the green dots, showing that the model is doing well at capturing the relationship between average temperature and yield. Despite average temperature being a weak linear correlation with the yield, my decision tree is still picking up on nonlinear patterns effectively enough to make effective predictions. So I chose to do this with the average yearly rain, which also showed the same trends, suggesting the model is very strong. And then next, I will use the model to make a prediction. I have the column names stored in a variable called feature names, and then I define values for those. To start, I use the associated label encoding value by passing the country, in this case Azerbaijan, to the transform function. along with the crop type, which is wheat, and then I pass those values to a variable called new sample, which holds my list of values for all of the features for all of the columns. So I've got 2025 for year, 1480 for yearly average rain, and so on. And then I pass new sample to a data frame to create the new sample data frame, and then I convert that using the transform function to standardize or normalize it into the same scale that the model expects. And then finally, I use that data frame to predict or make a prediction using the predict function, and that produced a value of about 46,000 HG per HA for a yield for these particular values. So in that way, I can make a prediction using the model. And then as the last step, it's usually insightful to visualize the tree. And so to do that, I use the plot tree function. And I set a max depth of 3, so you can see that here, 1, 2, 3. If I were to use the whole depth, it would create a really complex tree, which had a lot of overlapping values, which could be adjusted if you wanted to see the full resolution of that. But for this project, I decided to just show the main decision-making process at the top. And so we see those 3 layers here. This is what makes decision trees very useful and very transparent. You can see the actual breakdown of its decision making. And then to illustrate what happens if you don't set to max depth, I will show you the full decision making tree. And that looks like this. So you can see it got very complex very fast, but we could expand this out to see in great detail every one of its decisions, and that's very powerful when it comes to understanding how your model is coming up with its predictions. In conclusion, this project has been a rewarding journey in applying machine learning to an important real-world problem. I was able to take a dataset and explore it, clean it and visualize patterns, structure it appropriately to optimize it for machine learning, develop a machine learning model using decision trees, and evaluate its performance using different metrics. Importantly, it also has a real-world applicability and usefulness in predicting crop yields. Through each stage, I developed a deeper understanding of how to prepare data thoughtfully, select algorithms that align with a problem structure, and evaluate model performance using statistical tools and visualizations. Choosing a decision tree allowed me to handle categorical features and outliers effectively, and also kept the model interpretable. Most importantly, I saw firsthand how machine learning can be made useful for predicting crop yields and supporting smarter and more resilient food systems. Thank you so much for your time and interest in this project. It's exciting to see how machine learning can make a meaningful impact, and I'm glad for the opportunity to share that with you. Once again, thanks so much for joining me. My name is Leah Nicholson, and I hope you enjoyed learning about machine learning models and decision trees.